All right, welcome everybody to Wednesday. There's no class on Friday or Monday, so this is the last time you're going to see me before EU4 is due, your linked list assignment. So what I thought I'd do today is go over more complicated linked list functions with you guys. I'm pulling back up my linked list class that has a private node class inside of it. So the list itself has like push front, push back. It handles all the fiddly details with pointers and things like that. So the person who uses the list class down in main can call things like push back, push front, insert at index 3, the value 26, things like that. And it's going to be our job to get these functions written today. I'll just comment them out right now. We got a print function that'll print all the people in it. And we also need to do a destructor. The thing about the destructor is that we don't have a destructor, like if our destructor is empty, this is the destructor essentially that C++ makes for us. It just does nothing. Do you guys remember the rule for new? Every time you have a new, it needs to be matched with exactly one what? What's the rule? Every time you see a new, there must be one and only one, not two, not zero, exactly one what? Delete is correct, okay? So for a destructor, if we run this code, if we G++ this code and run it without a destructor, it seems to be fine. But the reason why it seems to be fine is because C++ by default doesn't do any safety checks. And this is something that I sort of philosophically disagree with, maybe. C++ defaults to fast and unsafe, and I would prefer it default to slow and safe, but, you know, such is life. So we have to turn on the address sanitizer. So -f sanitize equals address. ASAN for short is the name of it. And now when we run it, you will see we are getting memory leaks. We have a total of 3 objects that were allocated, and we didn't delete them. And you see down here, the pushbacks are, each one of those is going to do one new, right? It's going to new a node holding the data value of 10, and then one of 20, and then one of 30. And so we are leaking all 3 of those nodes. Our destructor is doing nothing. The goggles, they do nothing. Choose the form of the destructor. That's Ghostbusters. The other one was Simpsons. So what we need to do is iterate down the list and unallocate, free, delete every node in the linked list. And there's a couple different ways we do this. Just pull a little picture over here on. So we got a head. Head looks like it's kind of pointed here right now. Here right now. Then we got a tail. So what we want to do is we want to iterate. We want to delete this node. We want to erase this guy. And then this guy, then this guy, then this guy. And then be done. Okay? So anyone have any ideas how we could write code that would wipe out the first node, then the next node, then the next node, then the next node? What do you guys think? What if we just started with this? Delete head and delete tail. Is that good enough? Is this gonna do it? Well, we're only leaking one object now, so it's better, right? No? Yeah, all the things in between are still going to exist. Now, one way that you could do a destructor is that you could actually write a destructor on the node that deallocates the next person. And so you do like a recursive delete that way. But yeah, probably what we're looking for here is like a for loop, right? And so there is a pattern that we use. I covered this last time. I'm going to repeat it here. That we use in computer science to iterate down a linked list. This is as important a pattern, perhaps, as the standard for loop pattern or the range-based for loop pattern. And so it looks like this. So for node pointer putter equals head, as long as pointer is not null, pointer equals pointer points to next. And this sort of for loop you can do anything with. It's basically going to start at the top of the linked list, and it's going to stop the second it runs off the edge of the linked list. So this is like saying for each node in the linked list. That's how you would sort of understand this, you know, in English. For every node in the linked list. Now we might just want to do this, right? Just delete the pointer. Anyone see any problems with this? For every node in the linked list, delete the pointer, and then dereference that pointer we just deleted to go to the next element in the linked list. What's wrong with that? If you delete the pointer, you can't see what's next. Wrong. See, this is, there would be no more pointers to delete. Nope, we're trying to delete everything. Like the destructor gets called when this guy goes out of scope. And so we have to free everything that we've newed. We have to delete everything that we've newed, and that's going to be like right here. Okay. Now, if we write this code, and we turn off address sanitizer, doesn't seem good. If we turn on address sanitizer, you'll get more useful information. What we're getting here is a use after free. And the reason why we're getting a use after free is because we are dereferencing the pointer after we delete it. So you can see right here, we're saying delete pointer. Remember, in a for loop, that part of the for loop right there comes after the bottom of the loop is finished. So we delete the pointer, then we use that pointer to get to the next element in the list. And what's messed up about this is that it might work, right? Because here's something that students don't get about delete. It doesn't do anything, really. When you delete something, all of these guys are in RAM somewhere, right? When you say delete this node, it generally leaves it alone. Like it doesn't touch it. Head, this pointer here has some memory address, it's got some memory address, 420. Head is still pointing at 420, tail is still pointing over here. If you delete that node, all the bits in RAM at that address are still there. All that delete does, delete just marks the RAM to be reused. That's it. It doesn't erase a pointer. It doesn't zero. I mean, it could. It's undefined behavior at that point. If you ever touch RAM that's been deallocated, who knows what you'll get. But it doesn't have to do anything. It could just simply mark that spot of RAM as being available for the next new. And so maybe the next time you do new, it'll pick that spot and it'll just use that bit of RAM because it's already the right size for a node. It might just reuse it, or it might not. So this data might be here forever until your program quits, or it might be reallocated the very next time you call new ever anywhere. And so it's very, very dangerous to have a use after free bug, because here's the scary thing. It's not taking up any resources. No. You can think of RAM as like a giant array, right? And you've written something into an array, and then you've marked that part of the array as like, you can write there again. When something's newed, it's reserved for you. That whatever you put into that giant array called RAM, when you new something, all that you do when you new something is the system says, yeah, that's yours. Nobody else can touch it. No other program can use that block of RAM. That's yours. When you free it, all that happens is that block of RAM is marked as being reusable. And so somebody else might allocate it. You might, if you have a multi-threaded program, it could come in there and change it. But the really scary thing is it might work. Your code might work fine. And that is terrifying, because you would have a lethal bug. A use after free is a very, very serious problem. And you would just not know about it because it works. Your code works. That's why address sanitizer is life. Let me write this in a asan. Asan is life. Okay. If you have a use after free bug in your code, it'll detect it and it'll kill your program, and it will go fa 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 fa. Watch. If we run this code and with address sanitizer on, it will tell you you have used something after you've deleted it. This is very, very bad. Where? Line 39 of main.cc. That's where you screwed up. And the destructor was called for main.cc line 92. So line 92 is the very last, like the close bracket is line 92. right? And here's your destructor where you screwed it up. Okay. So yeah, it doesn't take up any resources. When you free something, those resources are now ready to be reused. So you can't reliably see what is after the deleted node because the node may or may not be intact and RAM correct. And the operating system oftentimes, when it has what are called dirty pages, which are pages that had been newed and then released, freed, the operating system will periodically come through and kind of like zero out. It's like somebody like just coming in and like scrubbing the memory like with soap and water. So the operating system will come in and kind of fill it with zeros for you. And so you can request a zero filled page of memory that's all nice and initialized to zero without having to zero fill it yourself, which is an order in operation. You just let the operating system give you scrubbed, sanitized pages of memory. So maybe at some point, whatever it is you deleted just vanishes, but you don't know, right? Who knows? Maybe it'll never get scrubbed because it might be still part of the page that you own. So it's extremely dangerous to have a use after free. And so this code here doesn't work. So what we need to do is, anyone have any ideas? Luke, any ideas on how we can maybe, I don't know, delete each person in turn without doing a use after free bug? Create a temporary pointer is correct. So we can just say node pointer temp equals pointer points to next. Delete the pointer and then say pointer equals next. So that is that. And we just need to go this here. There we go. And so this is temp. And this is a perfectly workable. I say that. Let me test it first. Perfect. Yeah, it's a perfectly workable destructor. Yep. Whenever you guys are working with linked lists, always turn address sanitizer on. -f sanitize equals address, because if you're working with linked lists and you have a double free, do you guys know what a double free is? Any guesses what a double free is? If you have a use after free, if you're leaking memory, address sanitizer is very good at detecting. It's possible to trick address sanitizer in theory, but in practice, it is spot on perfect. The updation could be yeah, all of the things. This is a thing. Infinite loop. So some people don't like writing while true. Yeah, any part of the for loop can be left blank. You do not have to fill out all three parts. So this is an infinite loop. And so some people prefer writing an infinite loop this way. I prefer while true myself. It just cognitively makes more sense to me. Yeah, if you forget like the semicolon, maybe like if you don't have the semicolon there, it's going to yell at you. So make sure you have the semicolon. You have to have the two semicolons inside of the for loop, or bad things happen. Okay. So yeah, so this is a perfectly good destructor for linked lists. This is a perfectly good constructor for a linked list. And the reason why it's a perfectly good constructor is because each one of the member variables are initializing themselves to 0. And by the way, this does not work in old versions of C++. So if you're using like C++ 98, you can't do this. Everybody tried doing it this way. Everybody thought it made sense to initialize your class's member variables when you declare the variable. But this is actually not actually okay in OG old school C++. Everybody tried doing it, and so they eventually added it because it just makes sense. And when you put an initializer there, essentially those 3 lines of code get copied and pasted into each constructor, if you want to think of it that way. And so if you have 5 different constructors, it'll copy and paste those 3 lines over and over again, so you don't have to repeat yourself. You're lagging? I'll say it again. You don't have to repeat yourself. You want me to say it again? You don't have to repeat yourself. Okay, so that is a destructor. That's very important. All right. So here we've got pushback. So that's going to add something. If we call pushback, like pushback 50, it would add 50 over on the right-hand side over here. But let's write a push front function. Who would like to volunteer to write a push front function? Somebody who's not AFK, ideally, on the chat channel right now. I will start off by making the observation that push front is probably going to be push back, but symmetrically opposite. Okay. All right, Olson, you are up. All right, so insert at the end, insert at the front. All right. So how do you like the case here when it's empty? So if we have a completely blank list, then we're allocating a new guy, and we're setting head to be the new guy, tail to be the new guy, and then updating size. Does that seem reasonable to, for push front? Basically the same as push back, right? Probably don't need all three of these conditions here. Probably just, if not, size. Seems fine unless it's empty. I didn't push check. Okay. All right. So case 2, then it's on an empty list. We know there's something there already. So let's snap this over here, snap this over here. Let's just see what we want versus what we're getting, right? So let's say we're going to insert to the front here. Let's say we're going to insert to the front here. I don't know, 76. Okay. So this is the new guy. This is the new guy. And we've got this list kind of like over here. So every time you draw something, this is why I like harp on students, like draw their linked lists. Every time you draw something, that translates into a line of code. So this line of code right here translates into this line right there. We just allocated a new chunk of memory. When you put ink on paper like that, and it's permanently on the paper until you erase it, that's new. Okay, but if you look at this, like head is not pointing in the right place. These pointers, currently this guy's pointing to null and previous is pointing to null. Right, so we need to link up some things, right? Okay, so the first line's fine. Now we're saying tail points to next equals the new guy. So we want to have the last person in the list, his next is us. Does that sound right? We should be messing with the tail at all when we're inserting at the front? What if we change this? What if we change this to head points to next? Is this going to be correct? This would be like the second person list. What should we do here? Head previous equals new guy. Very good. It's symmetrical. It is symmetrical. So instead of tail, we have head. Instead of next, we have previous. That which is first shall be last. That which is last shall be first. Okay, now new guy's previous equals tail. So what this is doing right now is this guy's previous is going to like point off around the world over to tail. Probably not what we want either. Currently, new guy's previous and next are both set to null. So do we want his previous? Now his previous should still be null, right? Because he's now the new head of the list, right? So what needs to change? New guy points previous equals null pointer. Previous should still be null. We don't need a line for that though, Luke, because the constructor sets both the next and the previous to null. So we don't have to set it. We don't have to set new guy's previous to null. Okay. So what do we need to change instead? New guy points to next. Again, it's symmetrical instead of the previous. It's going to be next. And equals head. And so what this looks like in the world of ink over here is new guy's next points to head. Perfect. And then we're still missing one. No, head's previous points to here. Cool. You see how each one of these arrows like translates into one of these lines of code. Now there's one last one. You can see here head is now not pointing at the front of the list. So instead of modifying tail, we should modify what? So we want head not pointing there anymore. We want it pointing at head. That is correct. So, or sorry, we want head pointing at the new head of the list, which is called new guy. Yes. Okay. So that, my friends, is a perfectly working push front. Okay. So heads. So you see, heads previous is the new guy. New guy's next is head. Head is now the new guy. Allocated RAM. Size plus. Looks good. All right. So top down here, do a push front, and now we should get 42 first because it's the new front when we print. 42, then 10, then 20, then 30. Yep. We should probably do both a forward print and see out. To divide them, we should do both a forwards print and a reverse print, just to make sure that all of our pointers are working both in the front and the back direction. And so we got 42 is in fact the front now, then 10, then 20, then 30. Going backwards, we get 30, 20, 10, 42. So it's correct. Always, if you have a doubly linked list, always test your code forwards and backwards. Because if you forget a backwards pointing pointer, then, all hell could break loose. Okay, so that seems pretty good. It seems like it's working. All right. So push front, push back. The only other thing we need to write is gonna be maybe a search. We can do search. Contains, I think. Yeah, he calls it contains. So, Sardarelli, you want to write the contains function? We can attempt. Okay, so for contains, like we want to say, hey, do you contain 20? And then what we're going to do is we're going to start at the head, and start at the head. New guy's not there anymore. So we're going to start at the head. We're going to make like a temporary pointer. Start at the head and be like, hey, do you contain 20? Nope. Okay, then go to the next one. Do you contain 20? Nope. Go to the next one. Do you contain 20? Yep. Okay, return true. And if you get all the way to the end without finding 20, you're going to return false. So what we're doing is we're doing a list traversal. We're doing the standard list traversal. We're starting at the head. We're going to the end, one node at a time. So this for loop here is what we want. But instead of printing the values, what should we have here? Instead of printing the value at each node, this is the data at the current node that we're on. We want to return up here. We want to return true if that data matches the key. We want to return false if it's not in the list at all. So what do I need to change here? So we're starting on the first node. If we get a match, if current node points to data equals key, then return true. What do you want to type here? We're searching. It's going to be order n, right? This is going to be an order n search. Because if you have a million nodes in the linked list, you're going to just go to the right, go to the right, go to the right, go to the right a million times, looking for the value. Thinking? Return something. All right, not sure. Okay, how about an if statement? So if cur node points to data, right? Cur node's pointing at the current guy. It's at first it's going to point to head, then it's going to point to the next one, then it's going to point to the next one. So if cur node points to data double equals key, then what do we do? So if the current node that we're looking at has the value we're looking for, what should we do? Return true is correct. Very good. And then what do we do if it's not a match? Return false. Now it seems like a bad idea because you're going to look at one node. If it matches, you return true. If it doesn't match the first node, you immediately return false. Return false bails out of the function entirely. Yeah, just go to the next one. The return false should only be here. Okay, you should only return false if you have made it all the way through the list and it's not there. Then and only then can you say, okay, it's not there. If you did it immediately here, then you would look at the first node and be like, it's not there. It's on the list. Bye. Yeah. All right, so that's perfectly working contains. And so we can check that you preemptively return false. Yeah, everyone does that. Everyone does. It's very common bug. So cout bool alpha does lit dot contains. Does it contain 30? And does it contain 31? So that should be true and it should be false. Good. Code's correct. Of course it's correct. I had no doubt in my mind it would be correct. All right, next up, we need to do insert in the middle. This is the hard one, okay? So we want to be able to insert something in front of index 3 in this case, right? So if you have 4 people in your linked list, the first one's 0, then 2, 0, then 1, then 2, then 3. Okay, and so we want to insert it before 3. So if we have 0, 1, 2, 3, then we're going to insert it between 2 and 3. So we want to put a 26 between the 20 and the 30. So 42 is going to be index 0, index 1, index 2, index 3. So we're inserting before index 3. All right, so let's go ahead and write that code here. So it's going to be void push at integer index, integer value. And so we are going to insert before index value val. Sorry. Insert before the index. The value val. There you go. Okay. Everything makes sense. If you have better variable names, tell me. Okay. So this is going to be an order in insert. Okay. Yeah. Very good, Kevin. Very good. Yeah. It is in fact order in insert. Inserting in the middle for a linked list can be order 1 if you have a pointer there already. Then it's easy. But this is going to start at the beginning and go to the right, 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 as many times as you have here. Okay, so we could be inserting this anywhere, and there's also maybe some bad values. So toss out some cases for me. Toss out some cases. For what input values would the input be bad to this function? String? Can't pass the string to it, so you don't have to worry about that. If the value is not in it, can't. The function only takes integers, so the type system will enforce that for you. Negative lists, a negative outside of the list, can't put something before the first index. You can, I guess, like 0, right? Like if you have 0, 1, 2, 3, then if you insert at 0, it'll go before 0. So that'll insert at the front. Okay, so negative integers are certainly not allowed though. So if index is less than 0, or if we have 4 people in the list, we can insert before 0, before 1, before 2, before 3, or after 3. So 4 would be allowed, I think, right? I think so, right? So if you're going to insert at... So if you have 4 elements in the list and you insert at 4, it would go after the end. It's like pushback, basically. So nothing bigger than the size, correct. Yes. So if index is greater than size, then we should throw, I don't know, runtime error or something. No, you're out of bounds. Okay, so good. Are there any bad values? Are any values? Are there any values for val? Are there any values for val that are invalid? Are there any values for val that are invalid? What do you guys think? Or can we take any integer as part of our, data payload? What do you think? All integers should work. Yeah, I think so too. I think we'll be fine holding any value. Okay, so we don't have to check for val, just for index, and that's how it is sometimes. Like sometimes, you just don't have any checks to do for a certain thing, and that's fine. Okay, so what different scenarios could we have for inserting into a linked list of integers? What state could the list be in that we need to handle? Probably special cases. Anything but negatives? No, I think we could insert negative numbers. I don't see why not. You can insert negative 20. Fine. Yeah, the list being empty is obviously a good one. So case number 1, list is empty. Okay. So how many other special cases do we need to handle other than just like we're inserting in the middle of the list somewhere? I can think of 2 other special cases that we might need to handle for inserting, because this allows you to insert anywhere. The lists don't fill up, so you can't have a full list. I guess technically we probably should be checking for running out of memory. That brings me back some nostalgia from writing programs on a 16 megabyte, system. Yeah, every time you called new, you had to damn well check to, make sure that you actually had the RAM for it. Nowadays, I think what are some other cases that we would have to special case? Because when you're inserting in the middle, you've got people on both sides of you, but not every insert will have people both to the left of you and people to the right of you, right? What are those 2 special cases? When there's somebody missing the node to the left, or there's somebody missing the node to the right. What do we call those? Insert at the beginning. Case number 2, insert at beginning. Case number 3, inserting at the end. And I think that covers it all, right? So you can either insert at the beginning, the end, the list is empty, or the middle, right? So all we have left is the middle. Inserting at mid. Inserting as mid. Okay. Could you just call push front and push back again? Yeah. Isn't that cool that we have those functions already? And in fact, they actually handle the list being empty, so we don't even have to special case that. Right, so we just say if size is 0. What's a shorter way of saying if size is 0? What's the C++ shortcut? Yeah, don't repeat yourself, right? Why should I rewrite code for push front and push back when I got it already, right? So if size is 0, or if we're inserting at index 0, right? If we're inserting at index 0, that means insert before the beginning, so it's push front. Push front, the value. Cool, we just covered 2 of the special cases. Inserting at the end. How do we detect if we are inserting at the end? Right, if we have 4 people in the linked list, 0, 1, 2, 3, we would be inserting at 4 to insert after 3. Not size. How do we tell that we're inserting at the end? So we can just reuse our code that we have already. If size double equals 3, size could be anything. Tail? Tail's a pointer, but we can do this because this is that's the index, right? So if they're saying like insert into index 7 and there's only 3 elements in the linked list, that's out of bounds. But if they try inserting at 4 or 3, yeah, equals size, correct. Very good. If index equals size, then we're inserting at the end, and we call push back value, and we probably want this to be an else if. All right, so we don't do both. We don't want to insert twice if there's one person, in the linked list. All right, so, or 0 people in the linked list, it would do it twice. Yeah. So we need an else, and then finally we can have an else block here. And what's really nice about getting here, is that we know we have somebody to the left of us, we know we have somebody to the right of us, and we know that our index that we're inserting into is valid because we have bounds checked. So once we get past the bounds check here, we know that our index is in bounds. And we know that we don't have to special case anymore, handling the beginning, because when you insert at the beginning, the head will move. When you insert at the end, the tail will move. When you insert in the middle, the head and the tail don't move at all. It makes our life really easy. We don't have to write code for messing with the head or messing with the tail. All we have to do is size. That's an invariant that we want to probably keep track on. Put it down here so I don't forget it. But yeah, it's nice. We know that there's going to be somebody left and right. Now, the first thing we have to do though, like if we have code like this, which currently has 5 people in it, and we're going to say insert before element 3. So like, let's say we're going to insert 26. We're going to insert 26 prior to index. This is index 0, index 1, index 2, index 3. So if the person says push at 326, which is I think our example, then this guy needs to go in between. Do you see this? Like 26 needs to make it between 20 and 30. And so every time, like I said, every time you draw ink on the screen, that is a line of code. So what line of code is this that I just drew here, where I am creating the node? And by default, its previous is going to be pointing to null, and its next is going to be pointed to null. So what is this called? When I draw a rectangle on the screen like that, what am I doing? I'm permanently putting data on the whiteboard, blackboard, I don't know, OneNote. What kind of C++ code is that when I allocate a new node like that? Yeah, node pointer new guy equals node val. Yeah. In fact, I can just come up here and just kind of just copy paste it. I don't have to retype things this way, right? And instead of new val, I'm just calling it val. Go me for consistency in naming variables. Okay, so we've allocated new guy. So new guy is up here. New guy is up here, and it's pointed at this node here. So what do I need to draw on the screen here? There's going to be 4 different pointers that need to get manipulated. So like if I say, hey, this guy's previous should be him, and I draw this like that, then I'm saying this guy. Oh, we need to get here first. We need a for loop, don't we? We need to actually find number 2 and number 3 here, right? The person to the left, the person to the right. We need to find these people, right? So how do we do that? How do we go 3 nodes to the right? 1, 2, 3. What kind of loop should we use here? Just for consistency. Both of these work, by the way. You can have the star attached to the type, or you can have the star attached to the variable. And both will work. They mean the same thing. In fact, you can have a space in between like that if you just hate people and choose violence. This is usually how I write it, node star, because I'm making clear that it's a node pointer. This is technically more correct because you can actually mix and match X star pointer to Y. You can actually mix and match regular variables and pointer variables in the same declaration. And if you did something like that where you have node star, you would think that everything's going to be a node star. Only the thing that has a star in front of it is a pointer. So this is probably the more correct way of writing your variable. But I kind of like this because it's, what is it? It's a node pointer, you know, whereas this is also node pointer, but it doesn't look like the type is node pointer, you know. Okay, so we need the type that finds which indices are 2 and 3. We need a for loop. That is correct. So it's going to be similar to the for loop we're going to use earlier, except we're going to use almost a regular for loop, right? That integer, because we're going to go to the next I times. So it's going to look something like this, like for int I equals 0, I is less than index, I plus plus. And we've got pointer in, so that number of times we're going to say pointer equals pointer points to next. So instead of traversing the entire linked list, we are going to go to the right index times. So if index is 0, we're going to stay where we are and insert in front of it. If index is 2, we go to the right twice and then insert in front of it. So if we pass in 2, pointer would start off here, then it'd point there, then it'd point there and finish. And then we would insert in between. But pointer here, the index here is 3. And so we're going to start here, go to the right, go to the right, go to the right, and finish with PTR. Pretend you didn't see that. So pointer is going to be pointed at 3. Okay. So when we start off, pointer is pointing here, and then 3 times we go to the right. So it goes 1, 2, 3, and finishes there. And so if we wanted, we could, I don't know, name these better or something. I don't know. Instead of putter, we could call it like right, our right friend. I don't know. And then we can have our left friend across the political spectrum. I don't know. Maybe we can have a pair of pointers like that. Left buddy, right buddy, left neighbor. I don't know. Give me some ideas for the name of the function. Right buddy, right friend. And then left friend, if we want to get left friend here, that's just right friend's previous, right? You guys understand? Lefty, righty, righty, tighty, I don't know. So we're going to make a new node pointer called left friend that's going to be equal to right friend's previous. Right-hand man, I like it. Okay, so we've got 2 pointers here. We don't technically have to do this. We could do it more obnoxiously with just one where you're saying this guy is previous is next is equal. It's just kind of easier to do it this way. You got left friend, you got right friend, and then this guy is going to be sort of like going to come in and hold hands with his 2 friends, buddy system or something. I don't know. It's like you guys ever went to Disneyland or something and you're in a group, you have to like have your 2 friends, and you have to hold friends with the person to the left, hold friends with the person to the right. Okay. And so now we need to make them hold hands. Okay. So we've got left friend, we got right friend, and now we need to make these pointers work. So let me do the first one for you. So right-hand man is going to, his previous is going to point to 26. Will the ones on the right and the left still point to each other? They do currently. And so we need to fix that because we need 26 to go in the middle between them. Okay. So here we go. So right friend's previous is equal to the new guy. Okay. That's this arrow right here. That arrow right there. Right friend's previous should point to the new guy. Now, for left friend's previous or next should point to the new guy. What do you guys think? Left friend's previous should point to the new guy, or left friend's next should point to the new guy? Next is correct. So left friend's next should point to the new guy. Better arrow. So left friends next equals the new guy. And this is why it's so important to draw things out. Every time you erase something and sketch in a new arrow, it's literally just a line of code. Okay. All right. So are we set now? Like if we go down the if we try printing the list now, are we done? We start at the head, we print out 76, go to the right, print out 10, go to the right, print out 20, go to the right, print out 26, go to the right, go to 0. Are we done? Or are there 2 more pointers we need? Yeah. So we need to set, correct, we need to set new guys previous and next. So what should this guy be? New guys next should point to who? That is correct, Kevin. Very good. So new guys next needs to point to right friend. Good. And new guys previous needs to point to who? Very good, Mr. Wallace. And then that, do you see how it's now fully connected? Like you can see it visually, right? Like now, you know, I mean, it's making a detour just because I didn't want to erase everything and move it to the right. But now everything's linked up properly. And that's why you want to print your list forward and print your list backwards, just making sure, you know, you didn't screw up the links somehow. Kind of like a ladder, exactly. So what do we say? New guys previous is equal to the left friend, left buddy. And new guys next is equal to the right buddy. Okay. That's it, we're done. That's the hardest function you'll have to write. Well, I've written it for you. The hardest function you're going to have to write is delete. Okay, and delete is very much like inserting. You know, you have to special case, what if you're deleting from an empty list? What if you're deleting from a list that has 1 element in it? You delete it from a list that has 1 element in it, the list is now empty, and you have to set head and tail to null. Okay. What if you have a list, you're deleting off the head, then head has to move to the right. What if you're deleting off the tail? Then tail has to move to the left. What if you're deleting from the middle? If you delete from the middle, then, well, I'm not going to do it for you, but I will give you the ink version of it. You are going to set, you can find left friend and right friend, you know, like if you had a pointer to the guy that you're going to delete somehow, then you can get the left friend by getting new guys previous, and you get right friend by getting new guys next. And then line 1, delete new guy. All that's been deallocated. Now you got 2 dangling pointers. We need to clean those up. So left friends next. Left friends next equals right friend. Right friends previous equals what? Right friends previous equals what? Equals left friend. That is correct. And that's it. Now it's been deleted. Look. I mean, if you don't like my twisty-turny pointer, fine. I think it's beautiful. You know, I'm putting it back. I don't even care. That is a beautiful, beautiful pointer. I've never seen a more gorgeous pointer in my life. Okay. Deal with it. But you see how it's linked up? Yeah. Person's been deallocated. That's 1 line of code. Delete new guy, or, you know, whatever you call it. I guess he's not a new guy at that point. He's an old guy. Yeah, whatever. You guys figure out the variable names because I can't. So we delete them. But remember, we had to get left friend and right friend first before we delete them. Otherwise, you know, your list is broken at that point, right? So get the friend to the left, get the friend to the right. And then after you delete the guy, then have left guys next be right, right guys left, right guys previous be left. You're done. That's the hardest function you're going to write in EU4. Yeah. The only trick to the delete function in EU4 is that you delete. So the user will say delete the first node with a value lower than X. So that's how EU4 gets you. Okay. So if you say pass in 30, then in EU4 you're first going to look at this guy. You're like, nope, he's got 76. 76 is better than 30. Go to the next. Is 10 less than 30? Yes. Okay, then delete that one. And so, once you found it, then you get left friend, right friend, erase the thing, fix the pointers, you're done. It shouldn't be that bad. Okay, you should be able to do that with code that's sort of the symmetrical inverse of what I just did with insert. Okay, all of the code that I have written here. Let's test it. Make sure it works first. Let's test it. Uh-oh. Insert at. Push at. Which one do you guys like better? Push at or insert at? I'm not. What do you guys think? Insert at? Insert at. Okay. All right. There we go. Okay. So we're inserting 26 between 20 and 30, and it worked. Both forwards and backwards. Okay. There we go. And so you can see what we did here, though, is we're reusing code. So whenever you write code, you have to think about all those edge cases. What inputs could be bad, right? And check for it. And then what different special cases, could our list be in? Like, empty is something you should always check for, right? Because if your list is empty, your head pointer is null, your tail pointer is null. And if you dereference them, if you ever say head points to data, like cout head points to data, and your list is empty, you're gonna segfault. Okay? If tail is null and you use tail points to segfault. Okay? So always think about, what if the list is empty? What if the list has one element? What if we're inserting in the front? What if we're inserting in the back? Right? And you just have to kind of like mentally go through each of the different possibilities that you could be inserting in. But the good news is, because I broke the problem down like this with push front, push back, we just reuse that code. That's really nice. So by the time we get here, we know we're not inserting at the beginning, so we don't have to worry about head. We're not inserting at the end, so we don't have to worry about tail. The only invariant that we have to maintain here is size. So don't forget that. And don't put it out. One student asked, well, why don't you put it here, right outside of this else block? Because now push front increases size, and we're going to increase size twice. Should be a mistake. So these two guys are already updating size, so we only need it here. And that is a for loop that will go to the right n times. Whatever index is, it starts at the beginning, and then it goes right once, twice, 3 times, 4 times, and then finishes. So that's another type of loop. Go to the right, go to the right, go to the right, go to the right, stop. Okay. That's it for today. So if you guys have any questions, if you want any help, hit me up. There's no class on Friday. There's no class on Monday. And then it's due the Wednesday, a week from today after it. So now's your chance to ask questions. So am I going to be around over the weekend? Yeah, you can hit me up anytime over the weekend. It's fine. Me and Crowley will be around. So, it's not like we're going to be, out of contact or anything like that. But I would say try and get it going right now. You got an hour left in class. Just make a good push on it. If you get confused, get stuck, hit me up. And I will answer any questions you guys have.